welcome to the 46th Moon Lectureship here at Angelo State University. I am very so we're opening the back doors, which is great. That means we have a good crowd today. Thank you all for coming out. I'm very proud and happy to be here. I'm very proud and happy to be a part of the Moon Lectureship for all these years. And because I know nobody wants to listen to me, I'd like to introduce one of my colleagues, Dr. Trey Hollick. Trey is an associate professor of physics. He's an ASU alum. He majored in physics and math here. After getting his master's and PhD from Texas A&M, Trey came back to Angelo State and then ditched us for some rinky-dink thing called the Fermi Lab in Chicago for a short time, but figured out pretty easily that Angelo State was a better place than that, and returned and works with us. He's a great researcher, has gotten many grants. He works with our undergraduate students and helps them become scientists and help them become physicists. And I am just so pleased to have him here, and I am so pleased to introduce him, Trey Hollick.
Thank you. I got introduced to Alex Filippenko. Phila double P Enko. There you go. What makes this man tick? To introduce him, I could mention his dozens of international prizes, awards, honors. I'm not going to do that. You've got that in front of you. I can mention that he's only the second person to among several Nobel laureates to be invited to give this lecture 2 times. I'm not going to do that either. I could say he has thousands of publications, public lectures, and over 50 years of pursuing science. Not going to say that either. Where did this giant, this astronomical giant, get his nebulous, his start, his spark, his fusion initiation? He gives this story, whenever he was 14, his folks gave him a telescope. And the third star he found was Saturn. And I'm like, dude, you're wrong. Everybody knows that to get a Saturn, you got to go to Lubbock or Dallas. That's the closest dealerships. To his credit, though, without anyone's help, though, and here's the crux of it, without anyone's help, he discovered that that star was really a beautiful planet with rings. That night, a 14-year-old freshman had his first discovery, his first eureka, his first blazing collision of ideas and observations, and he was filled with complete awe, chill bumps. And this is after many explosions and other experiments with chemicals. Like, this was the moment of a discovery, a mislabeled star planet. But this feeling has driven him this whole time. He continuously looks back as fuel for pressing on. That feeling has made all the sleepless nights that he's experienced worth it. I have the same story, but 1/30 of the publications. But I completely understand, and I have high confidence that some of you have that same experience, that same spark. Hold on to it. Learn from this man. Sit in awe, as I'm about to learn of the brand new physics from the James Webb. And remember that spark started all of this for him. And the spark in you will be the start of all of it that's yours. Ladies and gentlemen, Alex Filippenko.
Well, thank you so much for that very kind introduction. It's really great to be here. You know, I would tell that Saturn story occasionally in public talks that I gave even decades ago, and I thought it was unique And then people started coming up to me and saying, you know, the same thing happened to me. So did something vaguely similar happen to any of you, where you're looking through a telescope and you think you're just looking at some ordinary star and it ends up being Jupiter or Saturn? There's got to be someone in this audience. There is, yeah, did it happen? Right. No, it only happened to me, right? Yeah, you know, I was a budding young chemist at the time, from age 10 through 17. Chemistry was sort of my intended profession, and I did a lot of legitimate experiments, made synthetic rubber and Bakelite and things like that. But like many teen chemists, I was interested in explosives, small quantities, just small quantities that I would whack with a hammer and see what happens. And I had a number of explosions that probably could easily have taken away my eyesight had I not been wearing glasses. I was too dumb to wear a pair of safety goggles. So eventually, as a freshman in college, I decided, for various reasons, but including as an act of self-preservation, I've got to get out of this field because I don't have the self-discipline to stay away from the nasty chemicals. And a professor of astrophysics back then couldn't go to some supply room and ask for a bunch of chemicals, whereas a professor of chemistry could. I think things are different now even for professors of chemistry. Is that true? Any professors of chemistry here? Can you just go to a supply room and ask for whatever you want? Probably not, but I'd better turn on my little timer to make sure I don't go on too long. Anyway, yeah, it was science all the way, but that experience as a 14-year-old definitely started the path to astrophysics, and I still like chemistry, but I've never really looked back. It's been fantastic, and this has been a golden age of astronomy, and now we have this amazing telescope to talk about. So I just want to, again, thank the committee that chose me to speak for the second time in 2 years, you know, and in part it was because there was all this stuff going on in this area that was kind of astronomical. And I know a number of you were at my afternoon talk, and some of you were in my little evening thing yesterday and all that, so you've seen this a bunch of times, but it's a total solar eclipse. This happens to be one from 2023, not the latest one from 2024. But just to remind you of why it is that you saw what you saw, or maybe you didn't pay attention in your astronomy class or whatever, the moon gets in the way and can blot the bright part of the sun, exposing the hot, thin gases of the corona. And so this shadow lands on Earth, and it's really quite amazing. The sun is 400 times bigger across than the moon is, but it's also 400 times farther away. So they look the same size in the sky, the same angle. And it's not that 400 is some special number. You can do this with any two objects whose ratio of size is equal to the ratio of distances. So a tennis ball is almost exactly twice the diameter of a ping pong ball. I know it looks bigger, but that's because your brain is sort of evaluating the volume. But in diameter, it's nearly 2 to 1. So if I adjust these things so that the tennis ball is twice the distance of the ping pong ball, they look the same size in the sky. And that's what you have with the moon and the sun. And it's completely coincidental. There's no reason it had to be this way. So the moon casts a shadow on Earth, and that shadow moves along Earth at 1 to 2,000 miles per hour, and it traces out a path. And the paths are rare and narrow, typically covering 0.5 to 1% of Earth's surface. And so that means that typically you have to wait something like 380, call it just 400, same as the ratio of the sun and the moon. You have to wait 400 years before one comes to you. But remarkably, you know, one came to nearly you just a few weeks ago, right? There's San Angelo right there, and so you didn't have to drive far to get into this shadow. How many of you went from San Angelo into the pathototality and saw at least part of the total solar eclipse? Very good. That's wonderful. And for those who didn't, I hope you had a really good excuse, like, you know, your wife was giving birth to your first child or something, and that's perhaps a bit of a toss-up, and stuff. No, I don't tell my wife that. But anyway, yeah, we actually didn't go on a trip to Egypt in 2006 because the due date of our daughter was March 29th, 2006, which was the day of an eclipse in Egypt. And here I am, I'm an astrophysicist, and I don't know how to add or subtract 9 months correctly. I was never taught addition or subtraction or something like that, so yeah. Anyway, so I didn't go to that eclipse, but I've not missed many others once I got bitten by the disease. I've seen 20 of them, and I'm not 20 times 400 years old, okay? So anyway, you saw that one, which is really great. Here is my host, Jean-Anne Legrand's wonderful photograph, and then this is an amazing composite by Lee Childers in San Antonio, although he drove all the way to Arkansas to be in a region with more likely clear skies. Just beautiful tongues of gas there. You can see the prominences and things like that. But this is not a lecture on the sun per se. I just thought I'd rekindle some memories from a few weeks ago. And for those who didn't see the total solar eclipse, to hopefully encourage you to see one again, and you'll need to travel to a different country unless you're willing to wait 20 or 21 years, because the next one in the continental US is not until 2044, and it only goes over parts of Montana and North Dakota. The next one in the US to go over many states is in 2045, so 21 years from now. We're in for a pretty long dry spell. But you can travel the world if you have the time and means to do so, and see interesting places. If there's no particular order in which you need to see the world, might as well go to where there's going to be a total solar eclipse, because that'll be the icing on the cake, okay? Now, you might say, well, gee, I viewed on October 14th, I being you, an eclipse of the sun, but that's what's called an annular eclipse. It's a special case of just a partial eclipse, where the moon is a bit farther than average from Earth, and so it looks a bit too small to fully cover the sun, right? So you get this annulus. And that's an interesting curiosity and, kind of fun to see, but not a total solar eclipse. And yet, you had one here. There's the path, October 14th, 2023. And there's San Antonio. That was, most of San Antonio was just outside the path of totality, but within the path of the annularity. And San with the path of annularity, but slightly outside the path of totality. So how many of you saw the annular eclipse last October 14th? Yeah, that's great. But if you then thought that you'd seen an eclipse and there's nothing much to see on April 8th, and you chose not to for that reason, you didn't read the right articles, or the LLM in ChatGPT gave you, it was hallucinating or something like that, right? So don't tell me that you didn't go to the path of totality. I'll let you correct your wrongdoing in 21 years or so. So anyway, that's what you can do with an annular eclipse, but do try to go see a total solar eclipse. Yeah, it's kind of fun. You want to take a picture of that? That's not mine. It's Stefan Seip, but anyway. So you don't have to be too grumpy for an annular eclipse, but a total eclipse is much, much better. And I'm not just a lunatic, okay, right? It's a bit of a pun, right? Those of us who have seen total solar eclipses, ask any of them, and most of them will have a similar reaction. It's an indescribable experience that the photographs and stuff don't really do justice. You have to be there to experience it. Okay, well, onto the James Webb Space Telescope. It was launched after many years of waiting on Christmas Day 2021. We were initially hoping that it would be launched in 2007. So it was only 14 years late. But better late than never. Had it been launched in 2007, it would not have worked. And indeed, I didn't think it would work even when launched in 2021. And I'll give you my reasons for being a skeptic in a few minutes. So there are the inevitable comparisons with NASA's other great observatory, launched around 1990 or so, the Hubble Space Telescope, which has been fantastic for, 3.5 decades now. 3 decades really well. It had to be repaired for the first few years. It didn't operate completely as planned, but for 30 years it's been doing well. But now there's this new kid on the block, right? He thinks he's the center of the universe. I hate him, Hubble says. Webb is smiling, you know, in sort of a self-satisfied way. Well, yeah, sure, there are the inevitable comparisons, but as I'll show you, the Hubble is still very active, and I'm a Hubble hugger. Proposals for the next cycle, the next year of observations were due a month or two ago. I submitted a bunch of them, and then I submitted a bunch of Webb proposals as well, because as you'll see, they're complementary. But in what ways are they different? Well, first of all, of course, the Webb is a much, much bigger mirror than the Hubble. And so you can think of a telescope mirror or lens as being a gigantic eye. You look up in the night sky, your pupils dilate at night. That's to let in more light. Also, the cones transition to the rods, which are more sensitive to faint light, but not so sensitive to color, which is why sometimes in the morning in a darkened room, you might pull out a green sock and a blue sock and not realize that you put these socks on. At least that's what I do. And so actually I just buy a whole bunch of socks of the same color, so then it doesn't matter which socks I take. Anyway, you can think of a telescope as being a gigantic eye, and there's starlight raining down upon it, and it's collecting light. And so with a 6.5 meter diameter mirror compared to 2.4 meters for Hubble, the collecting area of the Webb is 6 times greater than that of the Hubble. And so it, per unit time, gets 6 times as much light, which means you can see, you know, fainter stars and galaxies and things like that. It's also got this gold coating. That's because of the infrared, which I'll talk about in a minute, all right? But anyway, it's a bigger telescope for sure. Now, speaking of the infrared, the Hubble Space Telescope is tuned to, operate at visible or optical wavelengths and also the ultraviolet, which is what burns you, right? Most of the ultraviolet is blocked by the ozone, the oxygen-3 molecules, but some gets through, so wear your sunscreen, and I own no stock in any sunscreen company, just wear your sunscreen. So Hubble looks at visible light and ultraviolet light, and the Webb is tuned more for the infrared, longer wavelengths than red, and that's what we often call heat radiation. So when you're by a campfire with coals and you're cooking marshmallows, sure, you see a reddish-orange glow, but that's just the tail end of the energy distribution, that which is visible to the eye. Most of the energy is coming out at longer wavelengths, which the human eye is not sensitive to. But certain animals, especially those that hunt nocturnally, are sensitive to the infrared. And so you're looking at infrared radiation with the Webb. And so, you know, observing at these heat wavelengths will tell us something different from observing at ultraviolet and optical wavelengths. And so in that sense, the Webb is complementary to the Hubble. It's not a successor. And I get peeved when, you know, there are newspaper articles saying that the Webb, Hubble's successor, is doing great things. It's doing great things, but it's complementary. And I can't fault the reporters too much when I even hear occasionally some of my colleagues referring to the Webb as the Hubble successor. I just get really annoyed, you know. How did you get a PhD, right? You know, it's complementary. Infrared, optical, and ultraviolet. They are different. They're the same electromagnetic phenomenon, but there are different manifestations of it, okay? So the next comparison is that Hubble is in a low Earth orbit. That was really advantageous because astronauts on the space shuttle could go and repair things that were failing and could replace aging instruments with new ones with better detectors, so it wasn't just 1970s technology. It kept getting better and better. And there were 5 or 6 such servicing missions. Not anymore, because our space shuttle program has been, it's not going yet, and on Musk's SpaceX and all that hasn't gone up there, and that's because there really isn't funding right now for a new refurbishment mission. But for 3 decades now, we've been using it, and it's been getting better and better. But being in low Earth orbit, it is subject to Earth's reflected light and also the heat, the warmth that Earth radiates. We all radiate warmth in the infrared because we're not at absolute zero or something. And so if the Webb were in low Earth orbit, the faint signals from distant stars and galaxies would be swamped by the infrared radiation from Earth, and the reflected visible light would heat up the telescope, and that would make it glow, and it just wouldn't work. So we needed the Webb to be in a very cold environment. So it was placed at a special place called the second Lagrange point, which is a semi-stable location. You can place an object there, and it'll kind of sit there for a while, and then gradually it'll wander away. But if you have a little bit of fuel with thrusters, you can gently shepherd it back into the L2 point, and it'll stay there. It's a semi-stable location. Now, you might say, why is this such a cold location? After all, it's 4 times the distance of the moon, but that's only 1% farther from the sun than Earth is. Earth is 150 million kilometers from the sun. The Webb is 151, call it. Big deal. So why is it such a cold environment? Well, it's not a cold environment on its own. But what you can do out there is shield the telescope from the sun. And this is an amazing feat of engineering. So the sun is down below, and you've got the hot side at 260 Fahrenheit degrees, and the cold side at negative 390, for a differential of 650 Fahrenheit degrees, because of essentially 5 bed sheets. Okay, yeah, that's what they are, sort of. I mean, they're not made of the same material, but they're really thin. They're called polyimide film, Kapton E variety. I don't know what that means, whatever. They're 0.025 to 0.05 millimeters thick, so they're really thinner, or as thin as bed sheets. And it's just this amazing stuff, which first of all reflects most of the sunlight incident upon it, but that which gets through then bounces around between the first and second layers. Oh, I meant to make my arrow big again, but I forgot to do that. Let me not take the time. And most of that radiation slowly leaks out the side, but some gets through, and then that bounces around and leaks out, and so on and so forth. And so by the time you get to the other side, 5 sheets later, you're at minus 260 Fahrenheit. So it's incredible, an incredible feat of engineering. I'm still astonished that it works, but it does. And these sheets are like the size of a football field. And the mirror is 21 feet in diameter itself, 6.5 meters. So you couldn't fit one of these things in a rocket. There aren't any that are that wide. So it all had to be folded up and stuck into a tin can the size of a school bus, let's say, something like that. And there was this elaborate unfolding sequence, which you can see here in an expensive NASA animation. And it's just wonderful to watch. And it gives me a chance to talk about this. It was estimated that there are 344 potential single-point failures.
The Solar and Heliospheric Observatory.
If things go wrong
in
that one place, the whole project is kaput.
It sits around these
and these are
halo
independent
orbits.
single-point failures, so you have to multiply the probability.
And so
Suppose
the Webb
each of them
is
had a
undergoing halo orbits
99%
as
chance
well,
of working correctly.
with
That's pretty good for government work, right?
Where it should be.
99%,
And that means
that
it's
was
not
good for
exactly
most
collinear with the sun and
But
Earth.
0.99 to the
Earth does not
344th
block
power,
the
folks, is
sun.
3%.
And so the solar panels
I
get
gave this
the
thing
power,
optimistically
the
a
sunlight,
3% chance of
This is all
working.
very clever.
And so I actually did not
astonishing
put
the
in
whole thing
proposals
works. Anyway.
for the first round
Oh,
a few
well,
years ago
the
because
mirrors
I didn't
were
want to spend a lot of my
unfolded,
time
and they were aligned, and here was
learning
the
about
first
how it
double-sized
exactly
image
works and
where
writing a
all the
proposal
mirrors
and
were
all
looking
this kind of
in the
stuff.
same place. Initially, they all kind of
But
looked in
I'm
different
happy as a
directions
clam.
and stuff.
It's working
And
better
people said ooh and ah,
than
and
expected.
most
Its
people said ooh
efficiency
and
is
ah
about
because of all these
25% better.
spikes and
Here you can
stuff.
see this
No,
triptych
the spikes
is
are awful
unfolding.
things.
The mirrors
ooh and
are
ah
unfolding
are
like
these
that,
faint
and
distant
it's just
background
marvelous.
galaxies and stuff.
I
and
tip my
collections of tens of
non-existent
hundreds
hat
of billions of
to the
stars.
physicists and engineers who
What
made
are the
this damn
spikes
thing
caused
work,
by, and what can we
because
do
I did
about
not
them?
think it would, but it
The
does.
spikes are what's
It's
called a
fantastic.
diffraction pattern.
So there it is.
When light interacts
And,
with the edge or a boundary,
still working well,
the hexagonal
and
mirror
we
here,
hope that no,
it bends
asteroid
around.
thing hits
There's
it
nothing we
like
can
that.
do about it, right?
So there's the
That's
observing
just the
side,
way-
which is cold, and then
way
there's the
nature of
sun-facing
light
side,
bends
which is hot.
around
And
obstacles.
you
So
want to
get the
see the
hexagonal
sun because
pattern
it's powered
of
by
these
sunlight.
hexagons here
There's
at
no
each of these
radioactive
parallel
material there.
edges. produces
like that.
these diffraction
Plus,
spikes.
there's a
And then you get
radio
another diffraction
transmitter
spike
and
here,
receiver, which
because
receives
although two of the
radio
struts
signals,
holding up the
commands from
secondary
Earth,
mirror
and also
are
sends the
aligned
data
parallel
back
with the
in the form
edges.
of bits.
So they add to the diffraction
So,
pattern already
So you
produced
have
by
this.
the edges.
You have to have this thing
The third strut
receive
of the
sunlight.
triangle can't be
Well, how does it
aligned
do that
parallel to the edge
if
of the
it's
hexagon.
collinear
Triangle
with the
and
sun
hexagon are
and
different
Earth,
geometrical
right?
structures.
Wouldn't
So that
Earth
what produces
block
the fainter.
much of the sun, producing a what? An eclipse, right? An annular eclipse. It turns out from the position of the Webb, Earth would block a good fraction of, but not all of the sun, so they wouldn't even be privileged to see the corona. Well, here's the deal in a diagram that's badly not to scale. Remember, L2 is only 1% farther from the sun than Earth is, not, like the same distance from Earth as Earth is from the sun. But the point is this. For reasons that are a little bit mysterious, I myself still have a hard time understanding the mathematics that goes into this. But at this L2 point, you can have what are called halo orbits. The thing just sort of goes around in little circles. And there's another so-called Lagrange point between the sun and Earth, and there are already spacecraft there. For decades, there's been SOHO. Fainter little diffraction spike right there. So if you're studying some galaxy like this faint little guy, and the spike happened to hit it, you can remove that light using software and stuff, but it'll add noise, and there's not much you can do about that. So you might ask for them to wait a while until this whole pattern rotates out of the way a little bit, and then that galaxy there will not be compromised by this ugly diffraction spike. So I'm going to show you lots of pretty pictures from the Webb, and you'll ooh and ah, but not at the star images. Stars don't actually have those spikes. Say, curse those spikes and ooh and ah at the things that are not spiky. Got it? All right, those are the rules of the game. All right. Okay, well, why study the infrared? I asserted that we can learn different things from the infrared than the ultraviolet and visible. Well, different wavelengths of electromagnetic radiation are produced by different physical processes. And to illustrate this, let me show you the visible light representation of a cluster of galaxies, a cluster of these bound objects, each of which has billions of stars. They look like these little smudges here, at radio, visible, and X-ray wavelengths. And what I'm saying here is important. This is the radio wavelength data, but so that you can see it, it's transformed to an optical color palette. All right, so different brightnesses of radio waves are made orange or pink or blue. And same thing with X-rays. We can't see X-rays. Maybe you're Superman or something, but whatever, X-ray goggles. But this is a color palette. And the same thing will be the case for the web. I'm going to be showing you infrared wavelengths to which our eyes are not sensitive, but there's a color palette. And keep this in mind whenever you see a web image in the press. What they usually do is they take the long infrared wavelengths, assign them to red, medium infrared wavelengths, assign them to green, and short infrared wavelengths, assign them to blue. So you get an RGB color image, which is a visible light representation of intrinsically infrared light. That'll be the case for every single web picture I show you, okay? All right, so the same thing here. So with visible light, what you basically see is the cluster of galaxies, all these things, and you're mostly seeing stars, collections of billions of stars. Great, all right, that teaches you there's a bunch of stars there. But at radio wavelengths, you see these two jets coming out and then a whole bunch of diffuse stuff in these lobes, and that's caused by a completely different process. Those are, without getting too much into the weeds, energetic electrons zipping around in magnetic fields, and that produces a type of radiation called synchrotron radiation, not the thermal radiation that our bodies emit or that stars emit. And you wouldn't have realized that there are all these energetic electrons there if you hadn't looked at the radio image, right? And then with X-rays, what you're seeing, again, are not the stars and not this radio emission or the same electrons that are producing it. Instead, you're seeing emission from a hot gas, millions of degrees, that permeates this cluster of galaxies. And again, you wouldn't have guessed necessarily that it's there. You might know something about the physics of clusters of galaxies and maybe postulate that there might be hot gas because all these galaxies are kind of wandering around and they're, compressing gas and make it hot. Whatever, you could be a theorist who postulates it, but there's no substitute for seeing something. And there it is with the X-rays. Same part of the sky, a million light years on a side. Okay? So those are examples of the same object at different electromagnetic wavelengths. And so similarly, we expect the infrared to teach us new things as well. Okay. So you'll learn new things. What's another reason for studying the infrared? Well, you can study the evolution of galaxies. Okay, so there are these big structures, 100 billion stars, 100,000 light years across, and a light year is the distance light travels in a year, 6 million miles. So if Earth were orbiting a star here and we're communicating with some alien creature over here with bits or maybe the English language, and we say, hey, how's it going? And they get the signal 100,000 years later, and then they reply, and they say, fine, how's it going with you? For a total round-trip conversation time of 200,000 years. That's not my fault, I'm just the messenger here, okay? This is just the way the universe is built, out of these giant structures. And the universe is filled with these galaxies, and so it's of interest. How do they form? How do they evolve with time? Well, by looking far away, we look back in time because it takes time for light to reach you from distant objects. You're some, tens of feet away from me, front row versus back, 100 feet maybe. So I'm seeing you as you were 10 billionths of a second ago or 100 billionths of a second ago, not as you are now. You may not even exist anymore. Oh, you do, good for you. You're still on this good earth. We see the sun not as it is now, but as it was a little over 8 minutes ago. That's not all that interesting. The nearest stars are some tens or hundreds of light years away. That's becoming more interesting. But if you look at galaxies that are billions of light years away, you're seeing them as they were billions of years ago. And so you can study how they evolve through time by saying that the galaxies of today, basically billions of years ago, looked like the galaxies we can see now, but from billions of light years away. Just like you assume that the babies of today will, become typical adolescents and then adults and so on. And you make assumptions about populations of objects. Any particular individual could be different. There it gets into the weeds somewhat, but you can study the populations of objects. So, to study the evolution of galaxies, we need to look back in time to a great distance and thus far away. But the universe is expanding, and that was the subject of one of my lectures 2 years ago. But it's still of relevance here. And the expansion of the universe takes intrinsically optical or even ultraviolet light and stretches it into the infrared, because the light isn't tied down. It's not like it's bound, like we're bound by electromagnetic forces and we're bound to Earth by gravity. But light just flying through space isn't bound to anything. So it stretches. So even if the stars back then, when they first formed, emitted ultraviolet or optical light, if they're 10 or 11 or 12 billion light years away, the stretching of the universe makes the light infrared. So the Hubble could not see the first galaxies or the first stars by looking at optical or ultraviolet wavelengths. We needed the infrared. And so one of the most famous first pictures during NASA's July 11th, actually it was July 12th press release, but they emitted a teaser on July 11th without saying much actually. But astronomers went agog, and you might say, yeah, look at this amazing thing here. Is that an alien or something? No, it's not an alien. There's a bunch of them, and we say yuck to all of them. They might have some planet orbiting them, and so maybe they're of interest to some of my colleagues, but yuck to all of them, nevertheless. What's interesting here is you see all these galaxies, and some of them look sort of more mature and older than they should have looked. We can tell that some of these galaxies come from when the universe was only 500 million years or so after the beginning, the Big Bang, and I discussed the beginning in my afternoon talk. But they look more well-formed and brighter and more stars and all that kind of stuff. They look like they matured more rapidly than expected, and that was really an interesting first insight. And by the end of July, professional astronomers had already submitted to peer-reviewed journals dozens of research papers on the implications of these kind of young yet mature-looking galaxies. So that's really very interesting, that Webb was already succeeding. This unfortunately led to some viral but incorrect headlines. The Big Bang didn't happen. There was this one fellow who used to be, a reasonable astrophysicist. I won't mention his name or anything, but he's kind of gone a little bit off the deep end in his later years, and I know that happens to a lot of us. I tell my colleagues at some point, if I start spouting nonsense, don't let me, speak to people or teach my classes or whatever. I don't think I'm quite at that stage yet, but so this person was saying these mature galaxies couldn't have existed, and so that means there wasn't a Big Bang. And this was just complete baloney. It was fake news. Don't believe it. And there were instantly some reasonable rebuttals by reasonable science writers. No, James Webb Space Telescope images do not debunk the Big Bang. JWST provides an intriguing look at the early universe, but it's not yet rewriting fundamental theories of the cosmos. Now, that was written quickly after that viral headline, so that was nearly 2 years ago. By now, we know enough from the Webb that it is rewriting some aspects of textbooks, but not that there was no Big Bang, right? There was a Big Bang, and quite a number of you went to my talk this afternoon. And this guy, Ask Ethan, he's very knowledgeable and writes quite good articles. And he says, has the JWST disproven the Big Bang? And no. Just no. You can't be much more emphatic than that, right? JWST has truly blown our scientific minds, but it's pure crackpot idea that the Big Bang is now disproven. The Big Bang, in essence, being the hypothesis that the universe started in its early days, for whatever reason, we don't know, but it started in a hot, compressed, expanding state. That's all the Big Bang theory in its simplest form says, and that is on very, very rock-solid evidence, okay? So going back to this image, what did it show besides these very young and mature-looking galaxies? Oh, and by the way, there's been some reasonable explanations now already been given, and one, I can go into this in more detail later on if you wish, but star formation is sort of a stochastic process in galaxies, and it depends very much on the density of the gas and stuff. And so some places form few stars, and some places form a lot of really massive, hot, luminous stars. And so what if the JWST is only picking out in its first, images those galactic outliers that had more than the typical number of really hot, massive stars? If we then assume that's what the typical galaxy looked like, then we'd be wrong. It's like going and watching a professional basketball game and assuming that a typical male or female adult is the height of the players. It's not a good assumption, right? You're looking at the outliers. And so that, to me, has been one of the more realistic proposals put forward so far. There's other ideas that maybe dark matter was kind of assembling gas and stuff gravitationally more quickly than we thought, blah, blah, blah. But there are other interesting things in this picture, and some of them were not completely unknown, and the Webb, indeed, has not just revolutionized everything, but helped confirm some of the things we thought we already knew with greater evidence. And one of those things is gravitational lensing and the existence of dark matter. So if you have a cluster of galaxies with visible matter and dark matter that holds the cluster together because it's attractive, and there's light that would have missed the cluster and gone off and missed your telescope in your eyes, but then it gets bent. I'll show you again the animation. It gets bent by the gravity of the cluster, and that then forms all these little arcs, these distorted images of the background galaxies. Let me just show you again, because this is another one of these expensive NASA animations, so we might as well use it. So there's light that would have missed our telescopes, but the matter in the cluster bends the light around. That's Einstein's warped space-time toward us, and it actually magnifies the images of the background galaxies and makes them brighter and hence easier to study. This is like the cosmos's natural telescope. It actually is allowing us to study some of the earliest galaxies that would have been too faint to study even with the Webb, but this gravitational lensing shows them more easily. And so the gravitational lensing is sensitive not only to the amount of visible light, but also to the amount of dark matter that holds galaxies and clusters of galaxies together. And this affirms the notion that there's about 5 times as much dark matter in mass as there is visible matter, like us and stuff. And it's still mysterious. We don't really know what it is. And again, we've known about it for decades, but the Webb data help confirm this. So that's kind of neat. Okay, the other thing we can do is we can spread the light out into a spectrum, a rainbow like this. And there are these dark lines here, and sometimes there are bright lines, depending on the physical process. And they tell you something about the composition of the gases in the object that you're studying. This is how we know, for example, that the stars are made out of the same periodic table of the elements as we have here on Earth. They're mostly hydrogen and helium, by the way, but they have trace quantities of other elements. So by looking at the spectrum, you can see whether 2 objects that are suspected as being the same really are the same, because you can see whether they have the same fingerprints. It's like astrophysical forensics or something. So I'm on a team whose theoretical modelers said that in this cluster of galaxies, there's these 3 pathetic little images, G1, G2, and G3. And my colleagues said those are gravitationally lensed images of the same very distant background galaxy. And you can tell from the spectrum where you plot brightness versus wavelength now, or color. Going back here and just imagine brightness versus color or wavelength. That's what we're showing here, brightness versus wavelength, going from short infrared wavelengths to long ones. And here, there's a pattern that trained spectroscopists recognize right away as being caused by doubly ionized oxygen and neutral hydrogen. And there are some other lines and stuff here. And all 3 of those little blobs have the same spectrum, so they really are the same object. And when we published this about a year ago, this was one of the furthest back in time, hence youngest of these galaxies. It was only 500 million years after the Big Bang at a redshift. I know there are some astronomy students here, Z of 9.51. We now know of some that are more like Z of 12 or something, which corresponds to a universe back when it was only 400 million years old. But when we published this, this was one of the earliest galaxies that had been spectroscopically confirmed, which was kind of neat, and we showed that these little blobs are indeed the same object, which is just kind of cool. But you know, the science is moving very quickly with the Webb, and we keep finding younger and younger ones, and it'll be really interesting. In the next few years, there's a real chance we'll see evidence of the very first galaxies and stars having formed. Closer to home, only 290 million light years away instead of billions of light years away, here are these 4 galaxies called Stephan's Quintet. There are 5, but this one is an interloper. It's just along the line of sight, but it has nothing to do with those. But these ones are gravitationally interacting, and they're even merging. You can see these 2 guys merging, and in the gas between these 2 or 3, where the gas is being compressed, this pinkish orange emission is caused by hydrogen that's been excited by a bunch of newly formed stars that came from the compression of gases in these clouds of gas, okay? So this is sort of showing what's going to happen to us and our nearest big neighbor, the Andromeda galaxy, in about 3 billion years when we start crashing into one another. Most of the other galaxies are so far away that they're moving away from us because of the expansion of space. But Andromeda is an exception. It's in our local group, our little cluster. We're gravitationally bound, and it's screaming toward us at 220 kilometers per second, something like that. And in about 3 billion years, it'll start to merge. Don't worry, be happy. Very few stars will actually collide, although planets could well be disrupted from their orderly orbits around stars. So, you know, we may be dislodged from our sun in 3 or 4 billion years, but by that time, the sun will have become so bright and hot that the oceans will have evaporated away. So we need to find another home before that. And then, of course, there are the asteroids to worry about and comets and stuff. But anyway, this merging process will lead to sort of a super galaxy. A few stars will have been lost by being thrown out of the system, but most of the stars will merge to form one super galaxy. And astronomers already have a name for it: Milkomeda or Milkdromeda, whichever preference you might have. Depends on how much emphasis you want to put on the Andromeda part of the name, Milkomeda or Milkdromeda. So, okay, here's another reason for looking in the infrared. You can see through clouds of gas and fine little particles that we call, you know, dust, right? You have dust storms here. If you've been to Burning Man in the desert of Nevada in August, you really know what fine dust is. Anyone here been to Burning Man? No? Oh, gosh. It's an experience, okay? Do it once in your life. If you really like it, do it more than once in your life, okay? But you can read about it on the web or whatever. Anyway, there's a lot of dust. And so, you know, for example, on a foggy day or, you know, cloudy day or when there's low clouds, you can't see necessarily an office building a few blocks down in Dallas or something, but you can still hear your favorite radio station. That's because the radio waves have an easier time going through the fog or the dust storm or whatever if you're on Dune, the planet of Dune, right? And the infrared can travel more easily than optical or ultraviolet light. Not quite as easily as radio wavelengths, but still more easily than optical and ultraviolet. And why that's interesting is that the process of stellar birth is often associated with clouds of gas and dust. At the star party last night, we looked at the Orion Nebula, where lots of stars have formed. And here's one of the most famous, iconic Hubble pictures, the Pillars of Creation, dubbed this because there are these clouds of gas and dust, and it had been widely speculated that there are stars forming there right now and recently formed. But we can't see them because there's so much of this dust that it's like a really smoggy day. It blocks our view. All right, so there's the visible light picture. There's the Webb picture. And it's the same overall structure. But look carefully, it's amazing. Look at this quartet of stars right here. Again, I apologize about the microscopic size of my arrow. I There is a way of using PowerPoint making it better. I just forgot to do that before I started. It's not at all obvious, actually, how to do it. But a student once taught me, and I gave them a bonus point. And then half the time I forget to do it before I start. But anyway, look at those ones right there. And then if you look at the visible light picture, they're not there. I mean, maybe that's one of them. I'm not sure. And then look at these ones here. Maybe that's one of them. Then there's a bunch here, and I don't know. I don't see anything there. And they're like stars throughout. And they're stars that recently formed in these pillars of creation, and now we can see them at infrared wavelengths. And again, this is a color RGB representation of infrared wavelengths. That's something that's often not mentioned in the news articles. So that's stellar birth. These really are the pillars of creation, and we can look at stellar death as well. Here's what will happen, broadly speaking, to our sun in about 7 billion years. It'll blow it out to become a red giant, and then the outer layers will gently be ejected away, leaving behind the inner, hotter part of the star, which then glows and makes the expanding gases glow. But in the Hubble picture, it was widely thought that this is the dying star. But now in the Webb picture, you see another one there, and it's closer to the center, and you can measure its properties and stuff. And it is more likely the dying star. It's just that the ejected gases formed a cocoon around the dying star within which dust particles formed and blocked the view at optical and infrared wavelengths. But there it is. I'm sorry, at optical and ultraviolet wavelengths. But there it is in the infrared. So that's the actual dying star there. And then my favorite dying stars are the ones that don't just gently erupt, but that literally explode in a titanic act of self-destruction. Here's an example of one that sort of set the whole field of supernova studies on fire when it was detected in 1987. It was a bit of a sleepy area of research before that, and then everyone and their grandmother started studying exploding stars because they're the origin of the elements that make up our bodies, for example, the iron and the calcium and the carbon and the oxygen. Anyway, here's one that's particularly nearby, only about 160,000 light years away. And it's been suspected that the ejected gases in these supernovas, these exploding stars, eventually start coalescing into these fine little dust particles as well, which, by the way, are not just smog and stuff, but they are critical to us because they are the regions where, new stars formed and planetary systems formed there. And if you don't just want gas giants like Jupiter and Saturn, you want a rocky Earth-like planet, well, that's going to be a coagulation of a whole bunch of little dust particles. And so we're interested in where the dust formed. And so with another team, I've been privileged to study a few exploding stars that we detected a couple of decades ago. Here's one from 20 years ago. And the Webb images reveal dust-emitting infrared light because it's warm. So that's brightness versus wavelength. You can see there's some signal here. It's not, zero. And you can even tell that although the data points are pretty sparse, this was a difficult measurement to make even with the Webb, the data follow the model for graphite dust grains. In other words, mostly carbon in little grains of dust. And yet we also know silicates form somehow out there. There may be other supernovae that form preferentially silicates. But the silicate model has this dip right here, which is not reproduced by the data. And so the graphite model fits better in this case. And so that was kind of cool. But we're seeing dust formation, in a supernova whose gases have only been expanding about 20 years or so, and that's kind of sooner than expected, so that was kind of exciting. Here's another reason to look at the infrared. You can see colder objects more easily because they emit infrared light. Now you might say coals are hot. What am I saying? They're cool. Well, coals are hot on a human scale, but they're cool compared to most stars. Coals are actually pretty cool. And so they emit most of their light in the infrared, and cool stars would emit most of their light in the infrared. So again, you've got this infrared light, which is lower energy per photon, per quantum of light. and tends to be emitted by cooler objects. And really hot objects tend to emit into ultraviolet. And our sun emits mostly visible light. It's no surprise that our eyes are tuned mostly to visible light. So here's sort of a representation of that. By the way, our sun is a white star. It's not a yellow star. It's usually portrayed yellow in kids' books and stuff. And even some professional astrophysicists I know think that it's a yellow star. It's simply not true. The spectrum peaks in the yellow-green part, but when you add the reds and the violets and all that, our eye-brain combination interprets that as white. Indeed, that is the definition of white light. And I'm not trying to be racist or anything like that here. It's just, it's a white star, not a yellow star. And I'm sorry if you don't like that. But anyway, it emits mostly in the yellow-green part of the spectrum. But a hotter star emits, a peak in the ultraviolet. So the Hubble is really good at looking at hot stars. But a cool star emits mostly in the infrared. And stars can be much cooler than only 2,500 kelvins. Our own sun is about 6,000. They can be down to 1,000 or 800 or something like that. And so their spectrum would peak way off in the infrared. For the astronomy students here, this is a really great review for your upcoming final exam, right? I'm repeating most of the things you hopefully know. So there's this weird type of star at the star-planet boundary. They're sort of more massive than 10 times the mass of Jupiter, or 13 times the mass of Jupiter, because at that mass, what you can have is a little bit of fusion going on in the middle. But it's not, so it's more massive than a planet, but it's not as massive as a full-fledged star where you can fuse normal hydrogen as opposed to deuterons, which are an abnormal form of hydrogen, has a proton and a neutron. And deuterons, it's like 1 part in 100,000 of hydrogen. But by the way, the study of deuterons is known as Deuteronomy. Haha, a little bit of a geek joke there. But anyway, so these things are not quite stars because they don't fuse normal hydrogen, but they're not quite planets either because they fuse deuterons for a while. And so they're called brown dwarfs, and they're not much bigger than Jupiter. And they're smaller than low-mass stars, and they're really hard to detect because they're cool and very, very dim, and they're just not visible at optical wavelengths because they don't emit much light. But here's an example of a new cold, distant brown dwarf that the Webb found. This is a filter which is, 0.9 microns. Now, your eyes can see up to about 0.7, let's say, microns in this unit. So this is called the near infrared, and there's just nothing there, okay? And, our eyes peak at around 0.5 or 0.6. But this is a filter, 0.9 microns. Sorry about the jargon here. Here's 1.15 microns. So this is farther into the infrared. And now, ooh, look at that. There's a thing that's there. And 1.5 microns, it's there. 2 microns, it doesn't look much brighter. But then, whoa, look at that. It's whopping at 3.56 microns and at 4.44 microns. So this is a very cool star. It's too cool to be a star. It's sort of too hot to be a planet. And so it's one of these brown dwarfs. And so now thousands of them are appearing in the Webb images, especially in regions of star formation like the Orion Nebula. So that's pretty cool. And then we move on to, closer to home, our solar system. My colleague Imke de Pater studies Jupiter and Uranus and things like that. And here's the optical representation of infrared light. Here's the great red spot, which here looks white. And the polar regions are colder than the equatorial regions, and so they have a different color palette. But whatever. There are all these storms and stuff. It's really cool. And Imke said something that NASA probably didn't want her to say. We hadn't really expected it to be this good, to be honest, said planetary astronomer Imke de Pater, professor emerita at UC Berkeley in a news release. Well, it's true. She's being honest. I told you flat out that I didn't even think it would work. I mean, she just said that we didn't think it would be quite this good, But anyway, so people are studying planets in our own solar system, and then here's a ground-based picture of Neptune with one of its moons, the biggest moon, Triton. And then here's Voyager when it flew past in 1989, and it discovered rings, or actually confirmed rings that we were suspected for other reasons were there. And now for more than 3 decades, the rings had not been seen because they're not really visible, at least not very easily, with a ground-based telescope. the ball of the planet is highly overexposed here. Here it is, actually. You can kind of slightly see the crescent there, and this is just kind of the overexposed thing. But then here's the Webb image. There's Triton with its awful diffraction pattern, yuck. So let me zoom in on Neptune so you don't even see Triton. There's a bunch of the moons, Larissa and, Galatea and whatever. But there they are. They're the rings, the old rings that are still there. And what's neat here is you can see a storm developing on Neptune. And so by studying storm development on other planets, you can learn something about climate here on Earth. Now, it's not a one-to-one correspondence. These giant planets don't have oceans of water, and they don't have continents and mountain ranges. And so Earth is much, much more complicated. Nevertheless, having said that, we can learn something about atmospheric dynamics and climate and stuff by studying other planets. And so this may have some actual practical applications as well as just getting kids excited about science, and most won't become professional astrophysicists, and that's okay. You don't need more than a few thousand of us running around the globe at any given time. But most of these kids will become, computer scientists or medical physicists or applied physicists or engineers, useful people, not just professors of astrophysics who are basically pretty useless, but other than exciting kids, okay? So, and then finally, because I'm running out of time and I want, time for Q&A as well, infrared spectra, making this rainbow stuff and measuring it quantitatively, the brightness as a function of wavelength, can reveal the presence of water and possible biosignatures of life, and even possibly technosignatures. And so here's the idea. Lots and lots of stars, most of the stars you see out there, are now known to have planets orbiting them. We are not at all alone in that respect. We don't know if there's life out there, but we know that nearly all stars have planets. And that's largely because of a satellite called Kepler, where they could observe these so-called transits. Most planetary orbits are along some random orientation, but a few of them are nearly directly or directly along your line of sight. So then the planet passes between the star and Earth once per orbit. And if you measure the brightness of the star, this is the brightness of the star now as a function of time, and 0 is way down in the basement here. Here's 0.98, 0.99, 1.00, 1.01. So 0 is way down there. This is quite deceptive. Only 1 or 2% of the light of the star is blocked. And in the case of an Earth-like planet, only 1/100% is typically blocked. But nevertheless, some is blocked, and that's what gives you this transit. And lots of people, or even amateur astronomers, are discovering transits now with crazy little telescopes, which are quite inexpensive compared to what I grew up with, and they can detect these planets that are transiting. And so the opaque ball of the planet is what produces this dip. But you see here a possible atmosphere, and the atmosphere is semi-transparent. It's transparent at many wavelengths, but at some wavelengths, the atoms and molecules will selectively absorb the light, okay? Producing one of those dark streaks that I had in the spectra I showed earlier. And so here, spreading out the light, you might see these absorption features that are in the star. That's fine. But if you measure the spectrum of the star outside of transit and then during transit, you might notice that, relatively speaking, some of the lines are stronger because there's a contribution of this absorption by atoms or molecules within the atmosphere of that exoplanet. So that would be a way of learning about the atmosphere, right? The overall strength is less because you're getting less light in a sense, but it's relative. It could be that those lines are stronger relative to that line. And indeed, this has been done even with the Hubble Space Telescope, precisely with that pair of lines I showed. This star with that phone number showed stronger sodium lines during the transit than not during the transit, and that indicated that there's at the very least some sodium in the atmosphere of that star, which is kind of cool if you think about it. Right? Okay, so what has the Webb done? And this goes, again, all the way back to nearly 2 years ago. And most of my examples have been from nearly 2 years ago because even in its first month already, the exciting results were coming out. And so since there was a greater chance that you may have seen them discussed in newspapers and stuff, I thought I'd highlight them. But all kinds of neat things are coming out. But here's a spectrum, brightness versus wavelength. And you see all these noisy dots. And it's a hard measurement to make, even with a big, huge telescope. But you can see a model here, this faint blue line. And it's fit through the data points. And the bumps and wiggles are caused by water. So that's really interesting. There's water in the atmosphere of this exoplanet. Yet this is the type of exoplanet known as a hot Jupiter. It's like the mass of Jupiter, but unlike Jupiter, which orbits our sun far, far away, 5 times farther than Earth. This thing orbits in just 3 or 4 days. So it's being blasted to smithereens by light from the star. And yet there's water surviving in the atmosphere. And it turns out that's not all that much of a conundrum, but it's still interesting to see water in that hot Jupiter. And if there's water there, there might be water nearly everywhere. And astrobiologists, those biologists who want to study the possibility of life elsewhere, they have a mantra: follow the water. Because all life on Earth, until the robots take over, right, the computers, all of biological life on Earth is based on water and, the chemical reactions that occur within water, a wonderful solvent, right? Now we've got these silicon chips that perhaps sooner rather than later, I never thought I'd say this in my lifetime, but it's actually a distinct possibility that they'll become smarter in some weird way, right? Students, I'm not encouraging you to use ChatGPT to do your English or history essays, but anyway, follow the water. And so if we find water in the atmosphere of an exoplanet, that becomes, sort of a signpost, a possible signpost for looking for life. And so then other astronomers will use other telescopes to try to find life. So that's kind of fun. And if we're really lucky, then we might see actual biosignatures and perhaps even technosignatures. So what I mean by that is the simultaneous presence of methane and oxygen, and this is a simulated spectrum. This is not a real spectrum of any object taken so far. This is what we hope to get. But the simultaneous presence of oxygen and methane would be interesting because methane oxidizes very, very quickly. So if you see it in the presence of oxygen, that means there has to be some more or less continuous process by which it gets created. Now, methane can be created by purely chemical processes that have nothing to do with biology. We see varying amounts of methane in Mars's atmosphere, and very few astrophysicists think that it's a good sign of life. Maybe there was life on Mars at some point, maybe not. We just don't know. But the methane itself on Mars is not that great a biosignature. But methane is also produced by what Carl Sagan called bovine flatulence, okay, right? Decay of living organisms and stuff. And so that would be an interesting place to look for other signs of life. And in a really good spectrum, we might see chlorofluorocarbons or something like that, right, that you get in refrigerators and stuff. And fortunately, those emissions have been cut down dramatically because they were eating away at our ozone hole. And that has been a science success story that was recognized, and refrigerators now don't produce so much of the CFCs. But nevertheless, it's a pollutant, and we might see such pollutants, technosignatures, in the atmospheres of other planets, which would be highly exciting. Now, this is admittedly a long shot for the Webb. This would be pretty ambitious. There's an observatory being planned for about 30 years from now called the Habitable Worlds Observatory, which is more likely, perhaps, to get these kinds of data. But it's not out of the question that we might get lucky and find signals for life from the Webb data. So, it's been fantastic, and initially, NASA set the bar low, after 5 years, declare victory. Now they're saying possibly 20 years, and that's because they aimed the thing so well at the L2 point that only a little bit of fuel was used up to nudge it into place. And that fuel is now left over to nudge it into place as it wanders away. If they had to use a lot of fuel to correct it and get it into the L2 point, then very little fuel would have been left over. But it's like you're a golf player and you're playing in San Angelo and you aim for New York or something like that, and you got a hole in one with just a little bit of help from one friend. You know, you cheated just a little bit instead of having a whole network of friends, you know, cheating along the way or something, you know. So it's anticipated to operate for 20 plus years. So imagine that, you know, in its first 2 years, not even that, it's been so exciting, and we're all tickled pink. And I'm, again, privileged to be in this whole field, and there are many, many forms of support that I've received from the federal government and from my university, and more so than ever before from private donations, which are funding science more and more and more, because the slice of the discretionary budget of the federal pie, you know, is becoming progressively skinnier because of all the mandates and all the societal needs. I'm not arguing against those needs, but it just means there's very little money left over. So I thank you for your attention, and I'll do some questions, but 2 years ago, some people asked whether there's anything they can get from me and take home. So I have a set of 12 lectures on black holes that you can get for $30 with a little guidebook, and I know not many youngsters have DVD players anymore. These are DVDs, old technology, but there is the guidebook, which I personally wrote, not with ChatGPT. And then there's another series of 12 lectures I have called Skywatching, Seeing and Understanding Cosmic Wonders. And they are phenomena in the daytime and nighttime skies, like rainbows and auroras and eclipses and things like that, and their physical explanations. And I have a whole bunch of these. They're not all that heavy compared with my textbook, which I don't have anymore, but I still would love to part ways with them. And so if you want one, you're welcome to come up after the Q&A. Thank you so much for your attention, and I'm hoping that we'll have some time for questions.